So let's come back to understanding mesons and baryons in this lecture. In the previous lecture, what we have been looking at the end of the lecture, we were looking at organizing all these discovered mesons and baryons into various graphical patterns. So these graphical patterns, if we remember correctly, actually these graphical patterns were similar to the ones which we have so just to show you the last time. So these graphical patterns were similar to the representations of an octet and a decuplet, which we have seen uh, in the representations of SU3. Now, in the representations of SU3, you can have you have these octets and decuplets which are represented in this nice fashion, and this is what we have looked at in the last. So these, for example, these baryons and mesons can be organized in very nice graphical patterns in terms of this representations of SU3. Say, for example, last time I showed you one example of this baryon octet in which neutron protons sit on the top and then sigma 0 sigma plus sit in the second row and the other one sits in the bottom row actually. Similarly, you also have the meson octet which also was covered in the last time. So when the meson octet has k and k plus in the first row with this strangeness plus 1, and then with strangeness 0 you have pi, pi 0, eta and pi plus, and s is equal to minus 1, k minus and k 0 bar. Now one interesting thing is this, because this is an SU3 representation, this, as we have seen, SU3 representations have layers over layers, essentially that there is a bottom layer and on the top of it there is another layer. So these, because they are sort of three-dimensional structures, so you can think that at the bottom layer there is this pi 0 and on the top of the pi 0 there is another layer, okay, where the eta sits. So at on each layer you can it's some sort of a spiraling, okay. This representation, the particle occupancy is some sort of a spiraling thing over there. So it keeps so at the bottom layer you have all these k's, pi's, and on the top layer you have some eta, and then further you can have other particles. Okay, but this is just an 8 representation, so there will be 8 particles. So this I think we also mentioned it during the discussion on SU3, that in SU3 representations, unlike the graphical representations of SU2, you have layers over layers. So you have further layers, okay, on the multiplicity. So there could be higher multiplicity at certain sites, and this okay. So this leads to layers of representation sitting on top of each other. So each representation would have layers. So there will be not just single representation at one side, there could be multiple representations. So with this, we saw these two meson octets and also the baryon octet. But still, the success came much, while this is a very fantastic thing, actually what Gell-Mann did was even further actually. He went further. He deduced that the mass difference between the different rows was actually same. So let me just give you the example. So another example. So in today's lecture we'll see another example. So let me start. So okay, so the another example is the case is the case of the baryon decouplet. So in the baryon decouplet, what one could organize is, suppose, let me just draw again using the various color coding which we had. This is q is equal to 0, q is equal to plus 1, q is equal to plus 2. So you can think of the baryon decouplet as this follows. Now let's write down the particles. This delta minus, delta 0, delta plus, it should be 1, 2, 3. Okay, I think I put one more extra. Delta plus and delta plus plus. Okay. The second line contains sigmas. One second, let me just write it down. Then we have again symbol 0 and then omega. Now this is the baryon decouplet. Now after organizing this, this particle was not found. Okay, it was not discovered at that time when Gell-Mann reorganized rest of all these things in a nice manner actually. So which this for example, what do you call it? So this particle was not yet discovered. Okay, was not yet discovered when Gell-Mann made this baryon decouplet organization essentially. So what he said, what he did was that he predicted the mass by showing that this mass difference, delta m, should be roughly equivalent to the delta m here. So this should also be roughly equivalent to the delta m. Okay, so there is a, so let me call it delta m, delta 2. So he used the delta m, okay, between these relations, and he had a nice interesting relation between the various rows of this baryon decouplet. Okay, and then he derived a relation. So the average mass of between the mass difference between each row would be somewhat the same essentially. So what he said, what he had was a relation which was like the following. So m delta minus n sigma should be equivalent to m sigma minus m this, okay, and so this should be equivalent to the mass difference between this, okay. So this is delta m 1, this is equal to delta m1. So he said that all the mass, okay, what he showed was that all the mass differences are average wise, they are the same, and with this he could actually predict the mass of the omega. So he has m minus m omega. So with this he predicted m omega, which was soon discovered actually. One second. Which was soon discovered, and this put this organization of mesons and baryons on a very strong footing. So this what it essentially did was that what it told you, okay, so all these representations are 8, 10 and so on, so there could be higher representations also, as we'll see, but at the time he looked at 8s and 10s, and with the 10 representation these are meaning he could predict the mass of the omega, which was soon discovered. So he predicted there should be a particle called omega with this particular charge, okay, and the strangeness of minus 3, and this was soon discovered. So he had the properties, its mass, its electric charge, everything predicted just from the organization of the mesons and baryons into these nice structures, which are actually representations of this SU3 group actually. Now, what is this SU3? What is a 3? Was the question which anybody could ask us at that particular point. Okay, but independent of talking about what this SU3 was, he could actually organize these things, and he could actually predict this omega meson, omega baryon, which contain 3 s quarks with strangeness of minus 3 and charge of minus 1, and which could actually be discovered. It was which this put. So this is the way to go. This actually gave the confidence that this should be the way to organize all the mesons and baryons. So one can. So there are other examples also. There are several examples which you can find meaning in, say, for example, in one of these textbooks like say Cheng and Lee. I think it's listed in the schedule in the book in the lecture notes I have sent you. Essentially, that what do you call the schedule of the courses. So where they have listed the textbooks and everything, course structure. No, I have given this. In that there is something called Cheng and Lee textbook, which I have listed. So you can find all these representations, essentially various particles which have been discovered, and this came out to be so this essentially put up this entire thing of this huge number of particles which were discovered, which were several resonances which have been discovered, into some organization structure. So this organization principle actually helped us to understand the structure of the bound states, various mesons and baryons. So these are numerous in number. Actually, you can look at it, and they started looking at some sort of a nomenclature for these mesons and baryons. The typical the PTG nomenclature is JPC, where J is the spin of the particle and P is the parity and C is the charge conjugation. Okay, spin, P is the parity, C is the charge conjugation. Okay, so this nomenclature you can actually see, meaning whether the particle is spin half or is a meaning it's a boson or it's a fermion, and whether it could contain what is its parity, whether it's a pseudoscalar or a scalar, or whether it's a pseudovector or a vector, and what is its properties under, say, for example, charge conjugation. There was some older nomenclature was also available, based on atomic structure nomenclature is also used, but okay, is also used actually. So there is also older nomenclature, because what people came to realize was that these are all bound states. Okay, these cannot be all of them. These all these several hundreds of I don't know, I shouldn't call them hundreds of mesons and baryons cannot be fundamental particles, right? Okay, they cannot be all fundamental particles. They are in fact bound states. So this is an important step actually, that you realize that these particles are essentially bound states. Okay, once you realize, okay, now then the question arises, if these are bound states and these can be organized in terms of higher representations of SU3, okay, if these are bound states and they can be represented, organized, I shouldn't say, I should say that they can be organized in terms of higher irreducible representations of SU3, one could ask the question, like, you know that SU3 has 3 times 3 bar, okay, it's like a product representation. Sim 3 bar is equal to 1 plus 8. So that means it's like similar to half times half in is equal to 1 plus 0 in C2, which is essentially means two spin half particles can either be in a triplet state or in a singlet state. Similarly, a fundamental and anti-fundamental in SU3 can the product of these two can organize itself into a singlet of SU3 or octet. So there you go. So okay, so you can organize it yourself into an octet. Now, okay, so you have, if something is there in a representation of 3 and 3 bar, the bound state of 3 and anti-3 bar could lead to an octet. So you have all these mesons which are organized in terms of an octet, okay, could be thought of as bound states of some 3 and 3 bar, okay, 3 and its anti-fundamental means 3 bar essentially. Okay, this gave the first hint essentially that you can organize these bound states into some triplets essentially, triplets of what they should be. The other thing also would be that you can have say uh, similarly you can have um, three. You also notice that 3 times 3 times 3 contains a 10 plus. So this is a decuplet. Okay, it contains a 10. So there is a 10 sitting in a 3 times 3 times 3. So what could be this 3? So this led to the idea of again Gell-Mann that there could be 3 quarks. Three quarks in nature whose bound states form all the mesons and baryons. Okay, so given that 3 times 3 bar contains 1 plus 8, so the mesons should be a bound state of quark, antiquark, and the baryons would be a bound state of quark, quark, and quark. Now, all that remained, so with this understanding, okay, all that remained was how to organize the various quantum numbers to get the wave functions of these bound states, essentially the mesonic bound states and the baryonic bound states. How to organize? So now we know that these quarks are essentially, you can fix the quantum numbers of these quarks essentially just from knowing the properties of the bound states. You already know the properties of the mesons. Say, for example, you know that there is a K meson which has a plus 1 charge, and there is a K meson which has a -1 charge, and then there is a K meson which is say for example which is 0 charge, so it's a neutral K meson. So you organize and your quark structure in such a way that the K mesons form these bound states in a particular manner. Okay, with quark anti-quark pairs. So these bound state wave functions can be are determined by the various quantum numbers of these quarks. So to first, so what are these various quantum numbers? So you have these various quantum numbers, means various compositions of this flavor of this quarks essentially. Okay. So let's okay. So one of the first quantum number which we see is essentially the flavor quantum number. What is a flavor? Flavor you can think is like a type. Okay, it is like a type. So each quark has its own flavor. So let's call this three. So let's call the quarks as say the three. There are three quarks in nature at that particular point. So at the like the okay, these three quarks are each have their own flavor. So what is the flavor of the quark? So for example, quark U, D, S. So this is the triplet of the SU3 essentially is given in terms of the flavor quantum number. Okay, the flavor quantum number of the up quark is upness, down quark is downness, and strange quark is strangeness. So the bound states which are made up of upness and downness do not contain strange quantum number. Okay. Similarly, the bound states which are maintained, which are essentially containing the strange quark, have these are what are strange mesons. So, say the bound states which contain the strange quark are essentially strange mesons and the strange baryons essentially. So these are do not contain strange. Okay, these do not contain strange. So now we can see that these bound states which do not contain strange are like, for example, let's take neutron and proton. Okay, and then proton state. The neutron has electric charge. So electric charge, and then it also has isospin I3, which we have seen essentially. So the electric charge of the proton is +1, isospin is equal to +12 minus half 0. Now with this we can organize the quark content of the neutron to be, it has no strangeness quantum number, so there is no strange quark for neutron and proton. Now if I organize the quarks in the following manner, of the triplet. So if I organize the quark multiplet in the following manner, say, so I organize in SU3 language, so I just wanted to uh, uh, write in the same fashion in terms of the strangeness and what we have seen earlier. So S is equal to S is equal to 0, S is equal to -1. Now I put 3, S is equal to 0, S is equal to -1, and then you have charge also Q. Now I give Q is equal to -1/3 and Q is equal to 2/3. Now I call the quarks which are having D is equal to -1/3 as D quark, S quark, because S quark should have its non-zero strangeness number, and then the quark which has a charge of electric charge of 2/3 AU. Now the electric charges and the strangeness and the flavor quantum numbers are related by the Gell-Mann-Nishijima relation as isospin, which tells you that Q is equal to the flavor quantum number, okay, plus or later it turns out to be something else which comes out to be hypercharge, okay, plus I3. Okay, so this is the organization. I3 is essentially the isospin. And the triplet of the SU3. So if the triplet of the SU3 is organized in this fashion, okay, such that it satisfies the Gell-Mann-Nishijima relation, and so that you can try to fit the data, because you have up and down quarks don't have any strangeness. Okay, so up and down quarks should be that way, and you should have two quarks, one having charge 2/3 and another having -1/3. The fractional charges, because the three quarks form a bound state, as we have seen here, that the bound states of baryons should contain baryons contain Q Q Q. So now we can ask the question how to organize the quarks in this particular fashion. So the baryons neutron proton can be organized in neutron would be U U D, and the proton would be U. Oh, sorry. D D U U D. So the neutron would be a wave function having one upness and two downness, okay, and the proton would be two up quarks and one down quark, actually, essentially. Now, if you organize the charges, electric charges of the down quarks to be so minus 1 by 3, minus 1 by 3, and the up type to be 2 by 3, you see that this has electric charge 0. And now you can see with this organization that the quarks also have assessment. Okay, quarks have assessment. So we will see that what exact isospin we will give to these quarks later on when we look at weak interactions, because we'll see that there is another interaction which is important to give the charge isospin assignments. I'll come back to this exact assignments of the isospins of the quarks later on. But for the present, let's just remember that when we are doing weak interactions. But as of now, let's just remember that the quarks have isospin. That's important to know. Now, coming to the mesons, so quarks we can give the multiplet 3 under the multiplet 3 representation, which is of SU3. Now, this SU3 is called the flavor symmetry. So this SU3 is called flavor symmetry. Okay, I'll come back to it in a second. Okay, 1 second, just to finish the organization. So it's under a triplet. So the three quarks are organized in such a manner that you can have neutron proton in this particular fashion, and the baryons which contain strangeness also form the decouplet which we have seen this morning. Actually, say for example, this decouplet also has a strangeness. So strangeness is equal to 0, means all the deltas which on the first row contain only U and D quarks, and strangeness is equal to -1 contain all the baryons with one S quark. Strangeness is equal to -2 means these baryons contain at least 2 S quarks, and strangeness is equal to -3 means the baryons contain 3 S quarks. Okay, so this has S composition. So the baryon decouplet composition, you can explicitly write it down. Okay. In this manner. Okay, just from the okay, what do you call? Just from the decouplet picture, you know what you can write down essentially. Further, based on electric charges, you also know the composition of the first row. So the first row would be starting with, say, for example, delta plus plus, meaning electric charge plus 2. So that means delta plus plus would have 3 U quarks, and then you have UUD, it's like a proton, right? Delta plus, and then you have it's like a neutron, UDD, delta 0, and delta minus would be DDD. Okay, so the 3 U quarks would give you electric charge plus 2, 3 D quarks would give you electric charge -1. So with this organization, you already know what this the first row would be, and you also know what is the second row. So just for the baryon decouplet, okay, the baryon decouplet. Let me just write down what we had discussed so far. So the baryon decouplet would be, so U would be then Okay, let's just write down all these things essentially. UUD, UDD, DDD. This is the first row. Okay. So this is delta plus plus, and this would be delta plus, this would be delta 0, and this would be delta minus. So notice that the 3d quarks means electric charge minus 1, 3u quark means electric charge is called double plus actually. The second row will start having one s quark. Okay. Okay, second row has three particles which are essentially having one s quark. This will be UUS, UDS, DDS. Okay, in the second row. Okay, this we called it as delta plus, delta 0, this sigma 0, sigma minus 1. This is the electric charge of any three dawn quarks would be always minus 1 essentially. Okay. Now the third row, okay, one strange particle, no, in the one strange particle, and then the third row would has two strange particles, and two particles which will have just two states, USS, DSS. Okay, this would have electric charge 0, this would have electric charge minus 1, just because of the charge assignments which we have seen. And the fourth row would have three down quarks or three strange quarks. Fourth row, three strange quarks, which is nothing but SSS, which is omega minus. Okay. Okay. So we reconstructed the decouplet also completely in terms of the fundamental triplets essentially. For the fundamental triplets, which are essentially UDS quarks. Starting with three quarks, we reconstructed the entire baryon decouplet, and also we can also do the same thing for the baryon octet, which contains a neutron, proton, and other things. Okay. With this, we started having some understanding that we can organize everything in terms of the quark picture, but still it's not complete because we also need to explain the meson picture in terms of quarks. So for that we need the anti-quark triplet, which is the 3 bar. So anti-quark triplet is nothing but the opposite of the quark triplet. So you have, instead of an inverted triangle, you have a what do you call it? A normal triangle. So where you have S bar. Sorry, you should. Let's assign charges. Otherwise, I'll get confused a little bit. So let me assign charges. Okay, Q. This would be, let me say, minus 1 by 3. Q is equal to 2 by 3 because it's anti-quark, so it keeps reducing. So this would be U instead of Q. What do you call U? It will be instead of D. And then I'll assign strangeness in green color. S is equal to plus 1, S is equal to 0. So this automatically tells you what your quarks are. Essentially, this would be your U quark. This would be S bar. Sorry, U bar. This is D bar. This will be minus 1 by 3. This will be D bar. So I have to be careful with the charges also. Here it should be minus 2 by 3 and then plus 1 by 3. So now you have an anti-quark triplet, 3 bar. Now you can construct the Meson octet. So the so you should have. So you can now construct 3 and quark triplet times an anti-quark triplet. So that give me a singlet plus an octet essentially. So this is a singlet and this is an octet state. So the octet is essentially the meson octet. So which we can form from this thing. That's right. We drew actually the octet cluster. Okay. So the octet would be again we'll start with the strangeness 0. If you remember the octet diagram. The meson octet had let me just draw here very smallly. So the meson octet had K0, then K plus, and then pi minus, pi 0, and then eta. Then there is pi plus, K minus, K0 bar. Okay, and this is Q is equal to plus 1. This is Q is equal to 0, Q is equal to minus 1. And now you have strangeness is equal to S is equal to plus 1. This row is S is equal to 0, and this is row is equal to S is equal to minus 1. This is K. K is equal to plus 1. This should be minus 1. Okay, this is your meson octet, and then so you can construct in terms of the quark picture. What would happen is that this would be a bound states of quark anti-quarks, right? So you have, so you'll start with the strangeness is equal to 0 again, like we always wanted. Okay, so we wanted pi 0. Pi 0 would be UU bar. Actually, it is UU bar plus DD bar. Okay, 1 by root 2. So you can have strangeness 0 also with UU bar plus DD bar. Okay, then UD bar, this is pi plus, and then pi minus is U bar D. Pi 0, pi plus, pi minus. Then what is eta? Eta would be something similar to pi 0. It is also neutral state, so it could be some DD bar plus higher state. So eta. So this, since it's a, if you organize it in terms of some so SPD and in terms of this atomic states, eta would be having a different. So I wish I could give, so you can look at PDG. for the exact masses and the nomenclature of it. So one should know this nomenclature, but meaning in terms of say uh, in terms of JPC. Okay, so I will not stick to it essentially. Okay, so the pi 0 is essentially an S state, and the higher eta is like a vector meson. It's a vector meson actually. It's a vectorial state essentially, which has higher angular momentum state. So this tells about the middle row, and now you'll have K plus, which is essentially this the first row. Okay, US. So, okay, then there is DS bar. Okay, so this is K plus. Okay, and DS bar would be uh, K0, and then K0 bar would be SD bar would be K0 bar, and then U bar S would be K minus. Okay, so 1 2 3 4 1 2 3 4. So this is completes the nonet octet 1 2 3 4 1 2 3 4. But there is also one more state actually, the singlet state. The singlet state. So this all the tick marks essentially octet state. They form the octet state, and there is a singlet state which is essentially you can have a heavier singlet state which would be SS bar, which is called eta prime. There are eta and eta prime form a very fundamental QCD problem. Uh, Actually, they had a very important implications for understanding of QCD. Okay, uh, which we will not deal with it here. Both eta and eta prime were extremely important to understand QCD. Okay, and for the present, uh, we will not deal with this as of now, actually. Okay, but just remember that there are these. So eta and eta prime have a very important and fundamental properties associated with have been extremely important in understanding our understanding of QCD. Okay, but we won't deal with them as of now. So this eta prime has also been discovered. It's a very important state. This is both eta and eta prime. Coming back to the quark structure, what we have seen is that all the mesons, all this entire higher representations of SU3 can be understood in terms of as bound states of the fundamental representations which form the quark. Okay, all the mesons and baryons organize themselves in terms of higher representations of SU3 in terms which as bound states of the fundamental representations which are essentially the quarks. The SU3 symmetry which we see is called the flavor symmetry. It's called the flavor symmetry. Now the way we organized again to revise this thing is that we start assuming that all the three quarks have roughly the same mass. So all three quarks have roughly the same mass. So three Dirac fermions have roughly the same mass means that there is some symmetry associated with that, and this symmetry is nothing but the flavor symmetry. And this flavor symmetry also tells you that uh, uh, tells you that these three quarks are roughly meaning this flavor symmetry, which is an approximate symmetry, also tells you how these three quarks form bound states, which are essentially your mesons and baryons. Okay, these bound states are nothing but your mesons and baryons formed out of these three quarks. Out of these three quarks, the mesons are essentially 3 times 3 bar of the meaning it's the quark anti-quark multiplied together, whereas the baryons are 3 quark multipliers put together. So you can actually build the wave functions in this particular fashion essentially. Okay, now we can push further this quark picture actually. We can actually push it much further and say suppose now ask the question, say suppose if this bound state picture is really correct, okay, can we have some sort of an empirical formulas or something which we can actually use to compute the masses of this bound states? Okay, okay, or say are these so I don't know the exact masses of up and down quarks, so maybe I'll know it later on. I can estimate it. We'll come to it a bit later. Okay, but if these masses are known to me, can I use these masses or the other properties using, say, simple formula like direct addition times some spin-spin interaction, like in what happens in uh, hydrogen atom, and then check whether this the quark model works actually. So how does it quark model work? Okay, so this was one can do that. One can actually do this kind of an analysis. We can actually write down a simple light quark, for at least for the light quark mesons. We can write down a simple formula. So for simple empirical formulas. And baryons. So the mass of the mesons, say for example, okay, can be thought to be roughly m1 plus m2 plus some factor a. We can try to fit this times a spin-spin interaction between the two quarks times m1 by m2 divided by m1 and m2. Okay. See, we already know what the meson masses are. One second. So we already know roughly what the meson masses are, and from those masses we try to get this picture. Why this uh, spin-spin interaction for all? We believe that the spin-spin interaction is the most dominant interaction, which would be um, responsible for modifying the meson masses and stuff alphabetically. Now this S1 dot S2, like in what we observe in a hydrogen atom. So half H cross square, okay, for S is equal to 1. So for vector mesons which are in spin 1 state, and S1 dot S2 would be, okay, minus 3 by 4 H cross square for pseudoscalars. Okay, so with this assumption we can try to actually use this formula, okay, and try to fit in the pi meson, what is a pi meson mass, and what is the, say for example, various um, uh, what is a pi meson mass, say for example pi 0. So for assuming, so for pi, now you fit A such that it gives you roughly a good fit to data. Okay. Similarly, you can also do the same thing with baryons actually. Okay, you can also do the same technology with baryons. The baryons would be the constant quark masses M1, M2, M3 times some constant A, again S1 dot S2 by M1, M2 plus S2 dot S3 by M2, M3 plus S3 S1 dot S3 by M1, M3. Now the spin products of three quarks, essentially S1 dot S2 dot S3, so that would turn out to be something like S1 dot S3 is equal to, so would be something like 3 by 4 H cross square and minus 3 by 4 H cross square for J is equal to 3 by 2 and J is equal to half. So J is equal to 3 by 2 is essentially the decouplet state, and J is equal to half is essentially the octet state. Okay, so you know this, and say for a value of A, you can actually fit the value of A, the data, and try to fit in the masses very well actually. You can reasonably fit the masses. So this A is not the same as, so let me call this A as A tilde, say for example. Okay. So if you pick up the A tilde would be something like some in terms of some other mass, say for example uptype quark mass or something, you end up having a good fit to the data actually. Okay, so you can do this business of adding the constraint masses and so the mass of the baryon. So empirical formulas tell you that the mass of the baryon or the bound state sum over all the masses of the constant quarks sum, this is sum actually. So plus sum over the spin-spin interactions. So if it is a meson, then it's only two constant masses, and if it is a baryon, it is three constant masses times the spin-spin interactions, all possible spin-spin interactions. Finally, the most important thing is something called the magnetic moments. So the magnetic moment is essentially the coefficient, or is defined in terms of q dot s term, as q times s, essentially the spin of the state. Essentially, mu is equal to q electric charge by m times s, essentially. So the magnitude of mu is equal to, so it turns out to be, okay, q by 2m, where s is equal to h cross by 2. So this is essentially the point of the, because these are all spin half particles, the constituents particles are all spin half particles. So we have for the same, okay. So for example, for each quark, say for example for the up-type quark, the magnetic moment would be something like 2 by 3 electric charge by 2 mu. Okay. Then down-type quark, the magnetic moment would be something like 1 by 3 minus 1 by 3 E, the electric charge, by 2 times m d. Similarly, you have for the strange quark, which will be very similar to that of the down type quark, except for the mass. Okay. Now, okay, there actually it's very important that the magnetic moment actually scales with the masses. The magnetic moment scales with the masses. That's an important aspect actually. So the dipole magnetic moment is dependent on the charge of the charge and mass of the quark, because the spin is the same. The spin, all the quarks are spin half particles. All quarks are spin half. Okay. So typically, what you would expect is that the magnetic moment of the baryon is mu baryon, which has in terms of the baryon wave functions, should just add up q1 plus q2 in terms of the baryon wave function sandwiched between them is the sum of the magnetic moments of the individual quarks sandwiched in the baryon wave function. Essentially, that means you have to compute what is the overlap of the say, for example, Q and quark in baryon, essentially in baryon wave function. Sandwiched in the baryon wave function. So let me call this as sandwich. So for all practical purposes, it's almost uh, uh, it's almost the same essentially. Say, for example, we all know what is the wave function of the baryon wave function. You can take it as u up, u down. So say, for example, for a simple baryon wave functions which we know essentially. So, for example, you know what say if it is UUD wave function. Uh, so you can actually uh, say for example okay, so if it is symmetric or an anti-symmetric, whether if it is UUD and um, if it is up type spin or down type spin, with that we can just sandwich it and we can actually find out actually. Okay, you can actually find out this baryon wave functions as some direct product of the flavor, the spin, and also whether they are fermionic or bosonic, and so on essentially. But this is not the entire end of all the quantum numbers. Okay, so there is one more quantum number which we have to mention now, which is called the color quantum number. So very important quantum number actually. This is an very important quantum number. Now, what happened was there were several bound states. Bound states found where the baryon has the same quark in the same angular momentum state. Okay, so if you have, say, for example, one of the states is essentially delta plus plus, which has UUU and it has a spin 3 by 2. So all the quarks are in the up state essentially. So if you look at the wave function of this one, this would be something like U up, U up, U up. Okay, so all the spins are in up direction. Okay, and this baryon has been found. So you have this kind of a state in which all the three quarks um, in the same spin. So are in the same spin state, and they are the same flavor, and they're all fermions. Three fermions in same spin state, uh, same flavor, and they're all fermions actually. This became an issue because and of the same flavor. Okay, the same spin. So everything is the same. Now, so this means that this violates, at the face of it, it violates Pauli exclusion principle. So you cannot have three three uptype quarks, all of them in the same spin state and in the same flavor. All of them are of course the same flavor. Okay, and everything seems to be matching with this. So this to avoid this, Gell-Mann introduced a new quantum number which is called the color quantum number. So the color quantum number uh, uh, says that all quarks come in three individual colors. Now, why do you need three individual colors? Because there are three fermions. So each of the fermions should be in a different state. So at least you should have three colors. Okay. So in such a case, what is it possible is that you can it's possible that each of these fermions could have a different color. Okay, color is like somewhat like a a higher thing like spin. Okay, higher thing like spin. Say for example, in the state which you have u, now you want all the three in different states. So you give a red color to the u quark, so blue color to the second quark, and green color to the third quark. And so what happens is that all the three are in different states and you no longer violate um, a Pauli exclusion principle. Furthermore, what you can do is that these three colors, because we know SU3 very well now because of all these things, these three colors can form a color singlet state. Okay, if we have there is always a 1, so 3 times 3 times 3, okay, is equal to 1 plus there is always something. Okay, so there is a singlet. So what Gell-Mann proposed was that anyway you know that okay, what Gell-Mann proposed, that if you have three different colors, because the quarks come in three different colors, so each of them can have three a different color at a given point of time and they keep changing, and such that the combination of these three is still a colorless object. The combination of the three is colorless. So the combination of these three colored objects again is colorless, and this is possible in SU3. Okay, the combination could be a colorless object, while individual parts could be having colors. So the quarks themselves have come in three colors each. Say up quark comes in three colors, down quark comes in three colors, strange knot quark comes in the same three colors. Okay, but then the combinations, the bound states of these three colored objects would be a colorless object. Okay, similarly, for the mesons, 3 times 3 bar is equal to 1 plus 8, say for example. We'll come back to this again and again when we do perturbative QCD. So this is also a colorless object or a singlet. Okay, so you can have a mesons in which you can have, say for example, the pi 0, or let's just take pi 0 or any other pi 0. That's a good example. Pi 0, which we wrote down as some u bar state, can be a color anti-color. So this can be, say for example, a red color. This could be red anti-color. Okay, so this is red, or let me only say is color. Okay, any of these three colors, color. This would be anti-color. So the mesons are not, they can also form, the mesons also can form colorless objects. So what we have seen is that so if you have this particular mesons anyway, doesn't have a need to introduce what do you call color, because as of for vector mesons maybe you have to introduce, but if there are of the same type, right? For example, spin if there is if the if they compose of spin 1 vector mesons, say for example, in the spin states are the same, then you may need to introduce. For example, for pi 0, the spin states are opposite to each other. U and U bar come in opposite spin states. So you don't really need to introduce a spin color quantum number. For other vector mesons, say for example, the flavor quantum number is typically different. Okay, and the flavor quantum number is typically different, but okay, you could have the same flavor also. Okay, for the baryonic bound states, definitely for the baryonic bound states, definitely we need to introduce the color quantum number, because all the three baryons could be in the same, the three quarks inside the baryon could be in the same spin state as well as the same flavor, and they all are fermions anyway. So everything is same in this case essentially. Okay. So for the baryon state, you can, where the example which we have seen, you can have baryons in the three same states, same flavor, and all of them are fermions. So you really need to, and they are, could be antisymmetric or symmetric, because depending upon whether they are scalars or fermionics. It depends upon how you organize the spin. Okay, so with this, you really need to introduce the spin color spin quantum number. Now, assuming the spin quantum number, so as I said, the spin quantum number, the color quantum number, anyway, will help you to understand uh, the baryon wave functions very well. Um, but they may not be as important for the Meson wave functions. It may look like that, but anyway, they are there. But it is important to know that both the baryon wave functions, the total baryon wave functions, as well as the Meson wave functions, could be completely constructed to be colorless. So this led to the idea that the color quantum number is invisible to us. Okay, so essentially all the objects in nature all the objects in nature are bound states of quarks such that they are all colorless. So that this sentence or this statement essentially that you in nature only those bound states are allowed such that they are all colorless is another word of saying that color is confined in nature, or there is something called the color confinement in nature. Okay, color is confined in nature. So uh, so this is the statement of color confinement, and because quarks carry color and they are not color neutral, okay, quarks carry color and are not color neutral, so quarks also should be confined. Okay, so they are not color neutral, so they also should be confined in nature. Okay, so because quarks carry color, and so that we have seen just now that we have introduced color for this quarks actually. So with this, the most general wave function, okay, of any baryon would also contain one more quantum number, which is essentially the color quantum number. So what we have seen, constructing a bound state wave function psi, let me use my black ink, psi bound state would essentially have the four quantum numbers, essentially psi flavor, psi spin, psi color, and whether that is essentially what Griffiths calls it as okay, as space, essentially whether it's what is its parity, and these aspects essentially whether it has even parity or odd parity. So these are essentially the main quantum numbers of the bound states of quarks. Okay, which we have seen. We have seen the flavor quantum number. We have seen the spin. Okay, spin is already known. So now we have introduced something called the color quantum number. So with this, we have come to some fundamental properties of quarks, of which form uh, the the building blocks of QCD. The building blocks of QCD. Okay, so all the light quarks, say for example UDS, can be used to understand all the light mesons, essentially all these mesons which are we have seen, which are essentially the pi meson, k mesons. These are all called the light mesons. These can be understood in terms of these nice structures essentially. Okay, so we'll look into a little bit more in the next lecture about the heavy mesons and aspects of understanding, how to understand how quantum field theory is built in these particular aspects essentially. I won't go into the details, but we'll only just mention a few things. Okay, and just to give you an overview of this particular topic. Okay, we'll continue this particular topic in the next lecture. Okay, I'll stop now.